So previous class we discussed about this phase shift full bridge DC-DC converter. So now we will discuss about this dual active bridge converter. So this one. So I have already given the introduction about this converter. So this is basically a bidirectional converter. So where its primary application is the solid state transformer, some kind of battery chargers, and other some applications in especially in microgrid applications or this renewable energy source applications. Right. So this is the basic circuit. So you have one side a H bridge inverter, on the other side you have another H bridge inverter. So this is DC, and this is also the output is also DC. If you want to use it for a solid state transformer, you have another one front end here, and you have another back end here, so that we have AC to AC power transmission can be taken place. So this is a high frequency link. So this is high frequency link. So usually this high frequency transformer, it's operating at a switching frequency somewhere between 20 to 200 kilohertz. So this is the inductor. So either this inductor is placed on the primary side or it will be placed on the secondary side. Generally, the this high frequency transformer, the size is very less. So when compared to this regular transformer, so this is for your comparison sake. So how much reduction in the size of transformer? So this is so here this one is the so one side you have this 50H 3 kVA transformer, so which is operating at a power frequency of 50H. So on the other side, so we have this 20 kHz 3 kVA high frequency transformer. You can see the comparison. So between the size comparison between these two. So both are rated for 3 kVA, but the operating frequency is, so one side you have 50 Hz, on the other side you have 20 kHz. The size will be almost reduced by 95%. So if you are going for higher frequency, instead of you are going for a 100 kHz or something, right? So in that case, again the size further reduced. So coming to this discussion, so this inductor, we usually place this side on the primary side or on the secondary side. So if we assume this is V1, right? So if it is assumed this is 1:n transformer, 1:n ratio transformer, so this will be NV1. So this will be NV1, and we have this output. If we assume this is output is V2, right? The primary voltage, if you assume it is V1, on the secondary side, so it will be NV1 because the trans ratio is 1:n. If you assume that. On this load side, see, we assume that the output voltage is V2. Because of this boost inductor, this inductor will, if you are placed on the secondary side, so it will act as a boost inductor. So therefore, we can expect that. So this NV1, so that is the secondary side voltage, and this V2, it may be greater than or less than. So it can perform both boost and buck operations. In fact, so it will be less than this NV2, or this V1 is greater than this V2. NV1 is greater than V2 depending on the operation. So we'll discuss more on that. So let us consider a simple thing. So where I placed the inductor on the secondary side of the high frequency transformer. So this is actually a relatively new area. So different papers will suggest different things. So in one paper, they place the inductors on the primary side, and one may place the inductor on the secondary side, and some may take N:1 transformer, and some other may consider N:1 transformer, and some other may consider one in the other way. Okay, so just we need to try to understand the concept. So you assume that this is the voltage, source voltage. So therefore, same voltage will appear on the primary side. If you assume that this is 1:n ratio transformer, So the secondary side will be NV1, and he assumed that the load side voltage is, or the load voltage is V2. The switches, this is Q1, Q4, Q3, Q2. So this Q5, Q8, Q7, and Q6. So generally it is known as bridge 1 or the converter 1, and this is converter 2. So we already discussed that. So when you have a diode bridge rectifier on the other side, the power flow between this primary and this one converter to other converter is happened due to the phase shift between these two converter outputs, right? So the converter outputs, the phase shift is created in case of diode bridge rectifier. So that is created by load parameters and the size of this inductor. So whereas here, so you can actually control the phase shift between these two converters. Right. So let us assume that, so this V2 is greater than this NV1. So that means it will operate as a boost mode. So this is operating as a boost mode. So this V2 is greater than NV1. So usually these two switches are operated together, and these two switches are operated all together, right? So here also this Q5 and Q8 are operated together, and this Q7 and Q6 are operated together, and there will be a shift between these two switching pulses. So we have several ways to control this dual active bridge rectifier. So one is the SPS, single phase shift, EPS, extended phase shift, DPS, double phase shift, and this is TPS, triple phase shift. Single phase shift, extended phase shift, double phase shift, and triple phase shift. So these are all the control ways. So first they start with SPS. So after that they have some drawbacks in the single phase shift. So they extended for extend this. They proposed extended phase shift. So after that double phase shift, and now triple phase shift. So come to this single phase shift control. Okay, so let us assume that, so these are the first converter switching pulses, and these are the second converter switching pulses. S1, S2, S3, S4 are the first converter, and Q1, Q2, Q3, Q4 are the second converter switching pulses. So usually this entire thing is one switching period. So this entire thing is one switching period, but for the control, to reduce the control complexity and for better understanding, so we'll take off of this one as one switching for the analysis purpose. We'll take off of the period, or this known as off switching period, for the analyzing purposes. So this S1 and S2, so we are S1 and S2, so operated complementary, and this S3 and S4, so there is a phase shift of 180 degrees between these two. Right, so we are talking about the single phase shift. Similarly, on the second bridge side, so we have this Q1, Q2, and this Q3, Q4. So this Q1 and Q3 are operated together with a complementary with Q2 and Q4. Right, so but there is a phase shift between these two. There is a phase shift between these two converters. Right, so we assumed that the phase shift is D into this THS. Okay, we assume that the phase shift is D into THS for this particular case. Okay, or D into, if we assume this is TS, some D into TS. So that's why it is known as single phase shift. You have only one phase shift angle, so between these two converters. So this is the H bridge, first H bridge output, and the second H bridge output. Okay, so we already discussed that. So depending on the voltage that appeared across the inductor, the current waveform will be, we can draw the current waveform, right? So in this case, right, the primary voltage minus the secondary voltage, so that is actually appearing across the inductor. So in this particular case, the inductor voltage is VH1 plus VH2, so up to here, okay, from here to here, so VH1 minus VH2, and whereas here, so it is VH1 minus VH2, and here it is minus VH1 minus VH2, and this is minus VH1 plus VH2. So the current is also, since it is from here to here, so its value is VH1 plus VH2, right? So it's actually VH1 minus of minus VH2. So therefore it is VH1 plus VH2. So therefore the current is increased from its initial value. So let us assume this is T0 period, right? From its value, right? So where this means the current is continuously increases. Okay. So here at the end of pi degrees, or at this point, this current will reach its peak value, and again it is reduces. So this is the point where it is touching zero voltage, it's a zero current. So this is the point where it is the current, inductor current touches zero value. So this is the point, so where this inductor current touches zero value. So this is about the single phase shift. So we'll discuss more on this single phase shift. So now come to this extended phase shift. So come to this extended phase shift. So here, right, if you can notice that, so there is a phase shift between this first H bridge. So you can observe the phase shift between the first H bridge. So earlier it is operating at 180 degrees. So now there is a phase shift between the first H bridge. Okay, and obviously there is another phase shift. So this is another phase shift between this first one and the second one. Okay, so we will discuss in detail about this extended phase shift. So come to this double phase shift. So here the phase shift within H bridge, so there is a phase shift, and externally means between H bridges, so there is another phase shift. So that means, so these two are operated in phase shift manner, and this is also operated in phase shift manner, and there is a phase shift between this 1 and 2. Okay, so that is double phase shift. Clear? If there is no phase shift within this converter, so it will operate at 180 degrees. If there is a phase shift, so there this pulse and this pulse, so there is having a phase shift, right? So here also this one is operating with another phase shift, and these two are operating with a separate phase shift. So usually this one is known as inner phase shift. So that means the phase shift that we are created inside one H bridge, so that is inner phase shift, and this between the two H bridges, so that is outer phase shift. Okay, so in double phase shift, the inner, right, so this inner phase shift and this inner phase shift, so both maintain same ratio with the outer phase shift. So these inner phase shifts are maintained the same ratio with this outer phase shift. So whereas in this triple phase shift, so that ratio is different. This ratio between the inner and the outer phase shifts are different. Okay. So we'll discuss some more on that. So first we'll start with single phase shift control. So this is corresponding to this diagram. Right. So this is corresponding, so the next waveforms are the corresponding to this diagram. So we already assumed that, so it is operating, this V2 is greater than this N V1. Okay. So why we are assumed this? So depending on the load conditions, so this initial value, so here this is the initial value, right? So this initial value may be negative, may be 0 or positive. Depending on the initial values, right, or depending on the load parameters, so this inductor current may be negative or it may be 0 or it positive. So usually under heavy load conditions, its value is negative, and in some no load conditions or light load conditions, its value is positive. So why it is like that? So we'll discuss in the later part. Okay. So just remember this much. For negative, so the load is usually heavy. For the positive thing, the load is usually light loaded. Okay. So this is the point. So where it is starting, and it is the point where it is reaches to 0. And here, right. So here, the switches are off in the second H bridge. So therefore it is increasing or decreasing. So that all depends on the how much voltage across the inductor is having. So this is the first case. So where we assumed that, so this is the initial current, right? So this T naught is the initial current. So that means this I of T naught is a negative here. So whereas this one, I of T naught is 0, and here I of T naught is positive. All these things are corresponding to V2 is greater than N V1. Clear? All these things are corresponding to V2 greater than NV1. You can see it here. So this is the point. So where it is starting. So this is, it is reaches to 0 here, and it's reaching to peak value, right? And here it is reducing. Okay, right. So here this magnitude, right? So this one, so it may be like this or it may be like this. It means the current may be, inductor current may be increasing or decreasing. So that all depends on this V2 and this NV1 relation. So this V2 and NV1 relation. So for this, so V2 is greater than this NV1. So therefore the current is increasing. If it is other way, the current will be, sorry, the current is decreasing. In the other way, the current will be increases. Okay. So this is the, so this waveform is the NV1. So that is the secondary voltage of the transformer, secondary voltage of transformer. And this is the load voltage. This is secondary voltage of the transformer, and this is load voltage. Okay. Secondary voltage of the transformer, and this is load voltage. So therefore its value is NV1 and its value is V2. So that means, so here we are talking about, so this is NV1, secondary voltage of transformer, and we have other side, we have V2. Right? So in the first case, right, so where is between, so this is the first case we are talking about. So this initial current, that is I T of 0, or this IL inductor current T of 0 is less than 0. So that means it is started here. So here which switches are conducting? The output voltage is positive NV1. So which switches are actually conducting here? To obtain, so this waveform, so which switches are actually conducting? to obtain a positive NV1 voltage across the secondary voltage, so which switches are actually conducting?
Q1, Q4.
Q1, Q4. So this is Q1 and Q4. So that means obviously this is Q2, Q3. So here to obtain a positive voltage, so which switches is supposed to conduct? So for positive voltage, so which switches are supposed to conduct? So here it is Q5, Q8, right? So this is Q5, Q8, and here it is Q6, Q6 and Q7 are conducting. So that means here also Q6 and Q7 are actually conducting. So but actual conducting or which device is carrying the current, so that all depends on its current polarities. Okay. So this is initial one. So this is T0 and this is the T1 point. So where the inductor current touches 0. Okay. So this is initial point. This is T0 point and this is T1 point. So we are talking about, so between T0 to T1 period, T0 to T1 period. Okay, T0 to T1 period. So during this period, both NV1 is positive and VT is also, sorry, this NV1 is positive and V2 is negative. So here this NV1, so that is positive and this V2 is negative. So this is negative, right? So during this period, so this is negative. So what is the voltage across this inductor? What is the voltage across the inductor? What is the voltage across inductor? So what is the voltage across this inductor? One side we have NV1, on the other side we have V2, right? So we have NV1 on the one side and V2 on the other side. So now what is the voltage across this inductor VL?
NV1 minus V2.
NV1, right, minus this voltage, right? So it will be minus of minus. So therefore NV1 plus V2. Agree? So that's why, so this is right. So if you notice that this NV1, we already assumed that, so this V2 is greater than NV1. So this V2 is greater than NV1. So therefore this height is small when compared to this one. Right. So this V2 is having, this height is more when compared to this one. Okay. So this inductor voltage, this is NV1 plus V2, right? So here in the first converter, so which switches are conducting? In first converter 1, so which switches are conducting here? Is Q1, Q4 are conducting. In the second converter, in converter 2, so which switches are conducting or which devices are actually carrying the current?
D6, D7.
Yeah, D6, D7, right? Since the current is negative, right? Since the current is negative, so here this D6, D7 are actually conducting. So even the Q6, Q7 are on, so there is no current flowing through that. So because the inductor current is negative. It's clear? Right. So at T equal to T1 point, right? At T equal to T1 point, the inductor current touches 0. At T equal to T1 point, the inductor current touches 0. Okay. So now we'll talk about this T1 to T2, T1 to T2, from here to here. So from T1 to T2. So from T1 to T2, right? So here this T2, so that all depends on the phase shift angle, right? So you assumed that, so this is the full cycle or one full means one full control period, right? So but for analyzing purpose we are considered only off cycle. So you assume that the off cycle period is TS. So this off cycle period is TS, right? So this off cycle is divided into two parts. So one is the phase shift part and other is the its control part. Okay, so this DTS is the phase shift between the two converters. This DTS is the phase shift between the two converters. So that means this angle between these two, right? So that is DTS, and the remaining period is 1 minus D into TS. Right. The phase shift is DTS. The phase shift, this phi is DTS. So this is 0 to pi, right? Or 0 to TS period. So therefore the remaining period is 1 minus D into TS. Okay. So now we will talk about, right. So this D2 is T2. This is corresponding to D into TS. This D into TS period. Okay. So in converter 1, so which switches are conducting here? Again, this Q1, Q4 are conducting. So here Q1, Q4 are conducting, right? In converter 2, so which switches are conducting now? Which switches are conducting?
Q6 and Q7.
Q6 and Q7, right? Agree? So earlier D6, D7 are conducting because the inductor current is negative, right? So now at T equal to T1, the inductor current becomes positive. From T equal to T1 onwards, the inductor current becomes positive, right? So therefore, the control, this means the current D6, D4, means D6, D7s are now commutated, and the current is transferred to this Q6 and Q7. The current is transferred to Q6 and Q7. So here also the voltage across the inductor is N into V1 plus V2. So that means here this is N into V1 plus V2. This entire thing is N into V1 plus V2. Clear? This is entire thing is N into V1 plus V2. It's clear? So this period, this entire period starting from T0 to T1, so how we will write in terms of equations? This period T0 to this T2 period, right? So how we will write in terms of, or the rate of change of this inductor currents? This voltage is V2 plus NV1 and its duration is DTS. So therefore, so we can write like this V2 plus NV1, this is equal to this inductor, this is LS into di by dt, right? So di by dt, the rate of change of this current is, so what is the rate of change of current?
Positive.
So this is delta ILS, right? That is the rate of change of current. So divide by this D into TS. Agree? So this is the voltage, is L into di by dt. Its period is dt. So we are talking about the entire thing, this T0 to T2. So here at I of T2, so this current at this point, right, the current at this point, so that is I of T0 plus I of T0 plus what we have, this DTS by this LS into NV1 plus V2. Is this correct? Is this correct? Is this correct? So this delta IL is, this is the thing, right? So I of T2 minus I of T0. Okay, so based on that, so I have written this expression. It's clear. This is the rate of change of current, right? So this I of T2, that's final value minus initial value. So from that, I have written this expression. Okay, so nothing complex here. Is this correct?
Yes,
This
sir.
expression.
Yes,
Okay.
yes, sir.
Right. So this is, assume this is equation 1. So assume, so this is equation 1. So now come to this third mode. So where it is T2 to T3. T2 to T3. T2 to T3. So in this one, right? So in this one, so it reaches the some value. So maybe it's maximum, right? In this particular case. So whether it is maximum or anything other value, so that all depends on that relation that we already discussed, that VT, if it is VT is greater than this NV1, so in that case we can get the maximum, right? So during this period, okay, at this T2, so which device in converter 1 is actually conducting Q1 in conductor, means in converter 1, which device are actually conducting Q1, Q4, right? Again, this Q1, Q4 are conducting. In this converter 2, so which device are in actually conducting?
Q5, Q8.
Q5 and, no,
Q8.
Q5. Yeah, this is Q5, Q8, right? Yeah. The Q5, Q8 are conducting, and the voltage across this inductor is, what is the voltage across inductor?
NV1 minus V2.
Yeah, this is NV1 minus V2. So this is positive or negative? So we assumed that this NV1 is, sorry, this so this V2 is greater than this NV1, right? So with this is positive or negative?
Negative.
Negative.
So this is negative, right? So that's why it is on, this is 0. So that's why it is showing in the negative term. This is voltage across inductor. So it is negative. Clear? So that's why it is negative. So therefore this current is reducing. Okay, so negative voltage across the inductor, so it is discharging mode, so that's why it is negative. So now you may understand, right? If it is positive, the current may be increasing, right? And it will reach the, right, it will reach the its peak value at t equal to T3 point. Clear? So here the current is positive, right? The current is positive. So which device are actually conducting here? Is it Q5, Q8 or D5, D8?
Q5, Q8.
Current is positive, right? So which device will conduct actually?
D5, D8.
D5, D8.
Sure. So which device will conduct? The diodes will conduct, right?
Yes, sir.
Okay. Is this correct? The diodes will conduct. Just think which one actually conducts here. Which one will conduct? No idea. Which one will conduct here? So this is the positive current, right? So therefore it will flow like this, okay? And through load, and D8. Agree? So which one now actually conducting here? Which one conducting now?
D5, D8.
D5, D8.
DI.
It's clear? So here the diodes are in conduction. Okay. So how you will write the expression in this case? How you will write the expression? So in this particular case, so we are talking about this T2 and T2 to T3 period. So during this period of time, the rate of change, so that is if we assume that, so this is delta ILS, so that is the inductor current, right? So its period is 1 minus D, correct me if I'm wrong, 1 minus D into LS into NV1 minus V2. Is correct?
Correct.
Okay. So from this I of T3, so this I of T2, right, plus 1 minus D into TS into LS into NV1 minus V2. This is the current, right? So next thing, so we have other modes. So we are now completed from 0 to this off cycle period TS. So 0 to off cycle period TS. So it is actually 3, we are divided into 3 parts. Right, we are divided into 3 parts. So where the inductor current actually touching 0 from its negative value, that is the first part. And in second part, from 0 to where it is reaching its peak value. And the third part, from its peak value to, right, up to the, okay. And this will be T5. And this point, so this is T6. So this one, so where you can get this 2TS period, that means the second off cycle period is completed or one full cycle is completed, right? So this is the timeline, because this is where the point where we are here. So this is the point. So both are same, right? So now it is touches to 0 at T4, and T4 to T5, it will reach its negative peak, right? and this T6, again it will come to this -1, right? This T6 value, right, and this T0 value, so both are same. So this is also equal to I of T0. This T6 value and this T4 value is 0. Agree? This is correct, right? In other words, this I of T0, so which is equal to minus of I of T0. This I of T0, so this is equal to minus of I of this T3. So this value, right? So this value and so the other T0 value, so both are negative, right? So again, this is the operational symmetry because that depends on the which device is actually conducting. So I don't want to discuss on that. So this one, right? This is required. Minus I of T3. So we have these three equations. This is one, right? So this is another equation. This is two. Okay. So we can solve these two equations. Right. So we can solve these two equations. We have another equations. If you can write this equation between this T4, for example, this T4 to T5. Okay, if you write T4 to T5, so can you write the equation for T4 to T5? For T4 to T5. So how it will be? One second. Just so between T4 to T5, so how this inductor current? So it is ILS, right? Okay. So how it will be? This is minus. So what is the voltage across this inductor? So this is minus of NV1 plus V2. So therefore you can write this period is DTS, right? This period is DTS. So that is minus DTS by LS into NV1 plus V2. Is this correct? Is correct? Agree?
Yes, sir.
It's correct. From T5 to T6, from T5 to T6. So what is the inductor current or rate of change of inductor current? So this is 1 minus D into TS, right? Into LS. Its voltage. What is the voltage that appearing across here? So this is V2 minus NV1. Okay, this is V2 minus NV1. So this is third equation here, and we have this fourth equation. So we have also this initial condition, it of 0 is minus of it, is that it 3, and also it of t1, so that is 0, right? It of t1 is 0, it of t4, so that is also 0. So by solving all these things, we can actually find out the inductor initial current it of t0. So it will be 1 by 4fs ls into 1 minus 2d, right? 1 minus 2d so it will be like this. One minus 4fl ls into ls, 1 minus 2d into v2 minus 1 minus 2d into v2 minus n v1. Okay. So this is the inductor initial current by substituting all its initial conditions. So we have also this maximum current, right? Inductor maximum current IL maximum. So IL maximum you can obtain from here, right? So that means this equation I of t2, so that gives you the maximum current. So that means I of t0 already known to you. So you need to add this additional term, this dts ls into nv1 plus n2. So we need to add this term. So now it will be 1 by 4fs ls into 1 minus 2d into v2. Just derive this 1 minus 2d into nv1 plus v2. So this is the inductor maximum current. So this fs, right? So this fs is the actual switching frequency, right? So this fs is the actual switching frequency. So we can have this relation, this ts is 1 by 2fs. Okay, so we are taking this fs as the off cycle frequency, right? So therefore this fs is 2 times the, so this 1 by fs, so this fs will move here, right? It's 1 by 2 times ts. Is correct? So fs, yeah, is correct. Okay, this ts is the off cycle period. This fs is the switching period or switching frequency. So these are the expressions for the inductor initial current and inductor maximum current. Inductor initial current and inductor maximum current. Right. So here this one is, we assumed that, so this is negative, right? So initially we assumed that, so this is negative, right? So this is the first case we are talking about. So that means where this initial current is negative. In other words, it is heavily loaded. So that means this is negative. So therefore, so this entire thing is negative. So this entire thing is negative. So that means this 1 minus 2d into v2, right? So this is less than nv1. So this 1 minus 2d into v2, so this is less than nv1, right? So there is a boundary point here, right? So where exactly these two are same. For example, this 1 minus 2d v2, so this is exactly equal to this nv1. So where we have at that point of time, this V2 will be 1 minus 1 by 1 minus 2D into NV1. Okay, it's clear. Let's see. So we'll review this again. So this dual active bridge operate in several. So this can be controlled. This is a newly introduced thing, right? Still some research is going on. So this can be controlled in different ways. So one is the single phase shift, extended phase shift, and double phase shift, and also some triple phase shift is also there, right? So we are talking about the single phase shift. In single phase shift, so there is a phase shift between the converter 1 and the converter 2. So that phase shift, right? See, we already means we normally control for the off cycle period, and we assume that the phase shift is d times the TS. The phase shift is d times the TS. So these are the normal waveforms. So this is the output of the secondary side of the transformer, and this is the load voltage or the load side output voltage, right? So here, this devices Q1, Q4 are conducting, and Q2, Q3 are conducting, and this Q5, Q8 and Q6, Q7 are conducting, and there is a phase shift, so that is DTS. So depending on the initial inductor current, so we have three, we can divide into three types. So one is the initial current is negative, and this initial current is exactly 0, and this initial current is positive. The initial current is negative, so it is usually happen at heavily loaded condition. So this is some boundary condition, and this is lightly loaded conditions. So this is negative here, and this is the voltage that appeared across the inductor. The voltage that appeared across the inductor. So we assumed that the secondary voltage, right? We assumed that this V2 is greater than this N1 V1. That means this converter is operating in boost mode from the secondary. Right? The secondary side voltage is NV1, and it is boosted to V2. So again, it is having three modes in each off cycle. So where this inductor current started from negative value to touching 0, from 0 to it's touching peak value, right? That is second mode. The third mode, it's peak value to at the end of the off cycle period. So during this period, in the first period, that is T0, T1, so where this inductor current is going from negative to touching 0, right? So we have this expression, right? So we have this expression. Okay. Again, this expression is also valid for, so when it is touching T1 to its peak value, T1 to touching its peak value. So during this entire range from 0 to DTS range, this inductor voltage is positive, so which is equal to NV1 plus V2. In the third mode, right, in the third mode, so where the second H bridge transition of switches is taking place, so in that case, the output voltage across this inductor will be, and this voltage across this inductor will be negative. So therefore, this current is reducing. This current is reducing. So under this case, the inductor current, so this is the expression for the inductor current, and this is the inductor voltage, so which is equal to NV1 minus V2. The operating modes are similar for the second off cycle, so which is starting from T3 to T4, T4 to T5, and T3 to this T5 to T6. Okay, so this expression, so which is valid for this T3 to T5. I think this is T3 to T5. So this is delta ILS minus of D into TS, LS, N into V1 plus V2. So this is the negative voltage will appear across that, and the current is also going negative. So this is T5 to T6. So where it is touching the peak value or negative peak, and it is reducing. So this is the equation. So we have some boundary conditions. This I of t0, so which is equal to minus t3, and I of t1 is 0, and I of t4 is also 0. So by using all these, we can find out the initial voltage or initial current in the inductor. So this is the expression for initial current in the inductor. Okay. So this initial current, so this is obtained from here. So this inductor current is obtained from here. So this I of t2, so this is the maximum current. So this is the maximum current. To obtain this maximum current, we need to add this I of t0. So with this expression, if we are adding this other term, so you can obtain the maximum inductor current. So, right. So we assume that this initial current is 0, means less negative. So therefore, this part is negative. Right, so that means the condition is 1 minus 2d into V2, so which is less than this NV1. So we have this boundary condition, so where this value is exact, these two values are this current is, and this I of t0 is 0. So under boundary conditions, we have this expression, this V2 is 1 by 1 minus 2d into NVI. Okay. If you notice that this expression is similar to a boost converter, this expression is similar to a boost converter. This V2 is 1 minus 2D, right, into NV1. So this NV1 is the input, and this V2 is the output, and this is the, right, this is the boosting factor. Okay, this is the boosting factor. So what is the maximum value of this D is 0.5, right? If you substitute maximum value of D, so under this case, what will happen? The maximum value, right? So therefore, you can theoretically, you can obtain the infinite voltage across the secondary or across the load. So this equation, it looks like a boost converter equations, isolated, non-isolated boost converter equation. So you have any questions here? You have any questions?
No, sir.